Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
She's now using queuing theory and some things from theory in really novel ways. And she consults for companies and stuff, and she actually does useful things with this. She's won a lot of Best Paper Awards, and you're the treasurer of Signetrics and the chair this year, and an NSF Career Award and stuff like that. Anyway, I am thrilled that she's here, and this looks like either you brought a child with you, or this is going to be an interesting talk. So what analytical performance modeling teaches us about computer systems design?
Hi, so I'm Maura Harkel-Balter. I'm from CMU. I'm going to be talking about performance modeling, which is the area that I work in. This is a pretty unrehearsed talk, so you should just stop and ask me questions because I might forget to say some things or explain some things. I was asked to give a tutorial talk, so I'm trying to keep this in the tutorial style, okay?
You bring like
so,
props with you.
yeah, well, you know, so if you're worried about these furry friends and stuff, you'll soon understand what they're all about. Okay, it'll all be happening soon. So I work in an area called queuing theory, and queuing theory is the study of queues and congestion and resource management. And it uses a lot of stochastic processes and stochastic modeling. It's pretty mathy. And this is an area that's been around for a really long time, okay? Maybe 100 years, at least 50 years of queuing theory. But surprisingly, it's not taught in computer science departments. And I don't really understand why, because computer systems are all about queues. If we didn't have queues, we wouldn't have any delays. Okay, so this is the area that I work in. And at CMU, we actually teach this in two different courses. We have an undergraduate course, 15359, and a graduate course, both of which talk about performance modeling and queuing theory and how to help in designing computer systems. And most of the stuff in there is very mathy and pretty deep. But what I want to talk about is stuff that everybody can benefit from and that anybody can understand in a 1-hour talk, and that people somehow surprisingly tend to forget. And so we're going to do that. So I'm going to start by just warming people up. So this is a queue, okay, and these are jobs that are in the queue, and some jobs are small and some jobs are large. When I talk about a job size, I mean its service requirement, which is how long it takes the job to run once it gets to the head of the queue. The head of the queue is here. This is the server. This is where the jobs get processed. And jobs are constantly coming in, and then they're getting served, and then they leave. They arrive at some rate. Let's call it lambda. This is the average rate that jobs arrive, maybe 3 jobs per second. And then they are served at some speed, mu. Okay, so maybe we can handle 4 jobs per second is how we serve them. Maybe they come in at 3 jobs per second at some average rate. And so we'll throughout assume that this queue is stable, and that the arrival rate is less than the service rate, and so things aren't going to infinity, okay? So there's some average queue length and stuff like that. And when a job comes in, like this blue job over here, the new blue job, it has some response time, and response time is the time from when the job arrives until it goes through the queue and the server, and then it's done. And so that whole thing is response time, and I'm writing here E of t, which is the expected time. Okay, this is it for math in the whole talk. You've got it, okay? E of t, expected response time. That's all you have to remember. All right? And these queues come up all over the place, so you can envision almost anything as a queue. A router is a queue, okay, that has packets. A supercomputing center is a queue, okay, where we're queuing up the jobs that are coming in from all over the world at the Pittsburgh Supercomputing Center. I work a lot in databases nowadays, so I'm very concerned with database lock queues where we have the transactions queuing up. Those tend to be first come, first serve queues. You're doing one transaction at a time in the lock queue. Okay, you're handling one at a time. A web server, I would consider a different type of queue. It's a processor sharing queue where you're sharing the server amidst many jobs, okay, and you're time sharing between them. So that's processor sharing queue, and we'll get to see all of those things. You guys can come on over and sit down, get comfortable.
We got a lot of
okay,
space here.
so we're up to question number 1.
Oh,
okay. Question number 1 for the talk. Okay, so question number 1, just to see who knows what's going on here, is suppose you've got one of these queues, whatever it is, your web server, your supercomputer, whatever you want. And what happens is you find out that this lambda, the average rate at which jobs are coming in, is now going to double. So instead of 3 jobs coming in per second, we have 6 jobs coming in per second. Okay, so lambda is going to 2 lambda. And you would like to keep your mean response time. Everybody remember what mean response time is? The time from when you arrive until you finish, the average over all jobs. You'd like to keep your mean response time unchanged. Okay? So the natural thing that you might think is possibility A, which is you should double your service rate. So if lambda is going to 2 lambda, then maybe you want to take mu and make it be 2 mu so that your mean response time comes out the same. Another possibility is maybe you need to more than double your service rate, because then, your mean response time will be the same if you kind of have to, put some extra oomph into your server, given that lambda is going to 2 lambda. And another possibility is you have to less than double your service rate. Who would like to tell me which is the right answer? And this does not depend on how the jobs are scheduled, and it does not depend on the job size distribution, although we often talk about MG1 queues, and it doesn't depend on anything. So if you're a physicist, you're probably at the best bet for coming up with an answer. But, okay, what is the answer? And we have this beautiful doublemint gum to go with our doubling answer. Anybody want to wager a guess? Yes. A, you want to double your service rate. Nope. Yes? C, the prize goes to the man in blue. Okay, now why is it C? Do you have any idea why C?
Well, because you didn't take into account here any of the variances.
Not really, not really. Okay, so pardon me?
Idle time.
Idle time? No, there is idle time. That's not really it. Let me explain it this way. Suppose you're sitting in a universe where lambda has gone to 2 lambda and mu has gone to 2 mu. Okay? Imagine now what that really means. So jobs are arriving twice as fast as they were, and they're being served twice as fast as they were, right? So you can imagine yourself having been moved into some kind of Star Trekian universe here, okay, where instead of doing the lambda goes to 2 lambda and the mu goes to 2 mu, you can just imagine every second becomes a what? Half second. Okay? So we're in a Star Trekian universe, and a second is really half a second. But otherwise, everything looks exactly the same. Okay? Because we're still working with lambda and mu, but a second is now a half second. So it's the same as taking lambda to 2 lambda and mu to 2 mu. Okay? So the queue lengths are all the same, but your response time, the time from when you arrive until you finish, is now in terms of half seconds. And so your response time will be half what it was if you double both. And so doubling both, going with choice A, was overcompensating, over-provisioning. Okay, we didn't have to go that far. There's a different factor for what you want to do, and it's less than 2. Okay? All right, because that was over-provisioning. All right, so this is how this talk is going to go. I'm going to ask you questions. I'm going to give out prizes. I don't have to do that much, right? Less than double the service rate. All right. So, impact. Be careful not to over-provision. You don't want to waste Microsoft's money. Okay, workload distribution. So something that's very important in queuing, more important than probably anything else, is understanding workload. And I've been spending some time talking to some of you about your workload problems. And workload has to do with what the sizes look like of the jobs. So some of you have this situation where you have some jobs that are very, very fast, like 0.1 seconds, and other jobs that are much slower, like 2 minutes, or even slower than that, tens of minutes. And so you have this huge variance in what the size or service requirements of jobs look like. So that's a very important thing in queuing to understand. So for a long time, people like to talk about job sizes as following an exponential distribution. And what that says is the probability the job size exceeds x looks like e to the negative x, okay? And it drops off very fast. And even if people didn't believe that that was the correct distribution, they used it anyway because it's easy to use. It's mathematically tractable, so why not? Okay? And more recently, in the past 10 years, tons and tons of papers have come out saying, this is completely wrong over here. Really, job sizes look more like this. Like if you look at Unix job sizes or supercomputing job sizes or probably Microsoft's job sizes, you have the probability that the job size exceeds x looks like a power law, like 1 over x. okay, which decays slower than the e to the negative x. Okay? Now, I'm not, you might be worried about this because you might say if it was 1 over x, that would be infinite variance, but it's truncated somewhere. Okay? But it has that type of shape, 1 over x, not e to the negative x. So first of all, this type of distribution has huge variability. Okay? And that's why it's a better model of computer jobs. Okay? Second of all, it has this notion of a heavy tail, which says that the top 1% of jobs comprise half the total load. So by taking that top 1%, the top 1% big guys, the elephants, and doing something else with them, you've reduced the load in half. Okay, you've cut things in half. So this has come up everywhere. Unix job sizes, supercomputing job sizes, web file sizes follow this distribution. This is a good friend of mine, Mark Curvella. He's done a lot of work on looking at web file sizes. They differ by 7 orders of magnitude. They have this heavy tail where the top 1% make up half the load. This distribution is also called the Pareto distribution because it has to do with money. And the idea there is that if you look at the 1% richest people in the country, and they were the only ones who pay taxes, that would be okay, okay? Because they have more money than all the rest of us combined. And this is actually true. Okay, that was the whole point of the Pareto distribution, is the top 1% have the money. But anyway, that's where it comes from. And it's actually true of human behavior, and it's all over. And so a lot of this talk is going to concentrate on this type of distribution, or any very high variability distribution, because that's what jobs look like. Okay, so to make things clear, we have a few questions, because nobody understands until the questions come. Okay, back to the exponential distribution, okay? In the exponential distribution, suppose your jobs come from this distribution over here. Okay, and you have these 2 queues here. Okay, one queue services jobs in first come, first serve order. So one job at a time, first come, first serve. Okay, and the job sizes come from this exponential distribution. In the second queue, the jobs are time shared, like in a web server, where the server is split between these jobs. So if there are 4 jobs, they're each receiving essentially 1/4 of the server, because we're kind of round robining between them so fast that essentially they're each receiving 1/4 of the server at the same time. Okay? So this is what some systems look like. This is what other systems look like. And my question is, which of these would give you the lower mean response time? Or maybe they're equal, or maybe they're, whatever, I don't know, okay? Which of these would give you the lower mean response time if you had an exponentially distributed distribution of job sizes? Because we want to understand. Anybody? Anybody? This doesn't have a prize, but the next question has a prize. Yes? The second one? This gives the lower mean response time, the processor sharing. Anybody else? They are the same. And in case you're wondering how weird could that be, that is the idiosyncrasy of the exponential distribution. Okay, I can explain this with Markov chains, but I'm not going to go there right now. Okay, but this is why the exponential distribution is so bizarre. Okay, is that it causes 2 completely different disciplines, scheduling disciplines, to actually be exactly the same. Okay, now we'll move the question and say, suppose you're going to ask the same question, but you're in the heavy-tailed world. So here, your job size come from this heavy-tailed distribution. Now, as a prize, okay, we have this authentic brontosaurus with a heavy tail coming from the Carnegie Museum. He was carted all the way here. Now, somebody must have like a little boy or girl, a 3-year-old, waiting for this brontosaurus. So think really carefully, okay? We are trying to minimize our mean response time. You have 3 possibilities. They're either the same, this one's lower, or processor sharing is lower. Which is it going to be? Okay, go ahead. Processor sharing wins. All right. Brontosaurus. All right. So processor sharing is, in fact, way, way better. And why is it so much better? Yeah?
If one of the queues stalls, you still get some progress.
One of the queues. There's only one queue.
One big job
right. If you've got one big job, it's not blocking all the little jobs. So the other jobs are getting through. And in fact, one could imagine that one might be able to minimize response time even further if one could somehow know which jobs were small and somehow let them through, right? Okay, so now we have another question. Oh, so the impact, by the way, is know your workload when you're doing your scheduling. Okay? All right, so here's another question that comes up. We have a time management book that goes for this question. Okay, so in this question, yes, a question back. Go for it.
How much faster is the other one?
Oh, so processor sharing can be way faster. So these were actually taken with real numbers. I mean, they look like they're just drawn in. But processor sharing can be way, way better than first come, first serve, and it depends on what the load is. As the load gets higher, the difference becomes bigger.
So it can be arbitrary high.
No. So a factor of 2 is the maximum you're going to get in waiting time between processor sharing and first come, first serve. But there's more improvement to come, because now, in addition to first come, first serve and processor sharing, I'm going to give you some other things like shortest remaining processing time or shortest job first or random. Okay? And now the improvement's going to increase a lot. Okay? The question is, how do these rank, okay, from low mean responsive to high mean responsive? Who has the highest mean responsive? Who's second? Who's third? And 2 of these things are equal. 2 of the things are equal. Okay? And we're again looking at our heavy-tailed workload. Anybody want to wager a guess?
SRPT.
Where do you want to put that?
Best.
Okay, SRPT is down here. And then what? What's the next one you want to put down? That's it? That's it. Okay, we got one answer. SRPT. Okay, anybody else?
Random and FCFS will be same.
Random and FCFS will be same. That's a good point. Okay, any policy that doesn't make use of the size of the job, okay, and is non-preemptive is actually the same. Good, and then what? Random and FCFS is the same. You're doing great. Keep going.
What is SJ?
Shortest job first. And whereas this is, sorry, I should say this, shortest job first, whereas this is shortest remaining processing time. So here you look at how much time you have remaining, okay, and it's preemptive. You constantly preempt. This is non-preemptive. You always just run the job that's shortest first, and then you run it to completion, and then you look for who's shortest and run that. Okay, so we have shortest job first and shortest remaining processing time. Random, you just randomly pick somebody out of the queue and run it.
What is the price?
Time management. Yes. Wait, you're doing so great. Can't you keep going? We have first come, first serve and random. Yes.
So I believe CFS and random would be the worst.
Okay, these are the worst. And then?
And then after that, it's going to be processor sharing.
No. Next. Anybody else? Go for it. Go ahead. First come, first serve and random are the worst. And then? And then SJF, even if it takes the short jobs into account and biases in favor of them, it's not preemptive. So what can happen? A long one. That's right. So it's bad, okay? And after SJF then comes processor sharing and then SRPT. All right. Pass this on back. Okay. All right. So that's actually what goes on here. So that's what happens here. This is the ordering, okay? And you might ask, well, what happens if you don't know the size of a job? Well, there what's customary is to use how long the job has run so far, which is the age of a job. So that's called foreground background scheduling, where you use the age of a job and you say, I'm going to run the job that has the smallest age so far. And in this type of a distribution, which has a property that I've been talking to some of you called decreasing hazard rate or decreasing failure rate, the age of a job is actually a very good predictor of its size. Okay? And so that policy, FB, actually would fit in here, close to SRPT. Okay? Just using the age of a job. And that's an important thing to know because often we don't know the size of a job. We just know how long it's run. And how close it is to SRPT depends on this hazard rate of this distribution. Yes?
The age will depend on the query system?
So age just means how long a job's run. So suppose you have some kind of Unix job or something, and say it's CC, and you've been running it for a while, and you see that this job has already used up 10 seconds of CPU time. Then for Unix jobs, that means it has probably at least half of using another 10 seconds of CPU time. Okay, once it's used 20 seconds, you know what? It has probably half of using another 20 seconds, okay? That is your decreasing hazard rate. Okay, that's what we're talking about. And distributions like that, which tend to be most jobs, have this property that this kind of policy is very close to here, and that's based on some work done at Berkeley that proved that type stuff by Rhonda Reiter. Yes?
Can you tell me, once my computer has stalled for 10 seconds, it's a good idea to switch it off?
Yeah, it's a good idea to switch it off.
This call is very important. Please keep waiting. You should hang up.
Okay. So one more thing I'd like to just add from a research perspective about this SRPT is that many people are afraid of doing policies like shortest remaining processing time. And the reason that they're afraid of these policies is because of what? What scares people about, what scares you when I say, let's put all your short jobs first? Starvation of the long jobs. Well, that too is a myth, okay? So in 2001 and 2003, I had a few papers at Sigmetrics that said that this whole thing about starvation, this Klein-Rock's conservation principle, you help the shorts, you hurt the longs, you help one person, you hurt the other person, not true. Okay? Klein-Rock isn't wrong, by the way. His papers were all correct. We just misinterpreted them. So, okay? So we just overextended ourselves in interpreting what the paper was saying. What really happens is you can have a policy like shortest remaining processing time that helps the short jobs. And it can do so without hurting the long jobs. In fact, the long jobs can do better too. So if you're comparing SRPT, shortest remaining processing time, and processor sharing, what the exact theorem should say is every single job can do better under SRPT than under processor sharing, provided the load is less than half. But every single job in expectation can do better. Every single job size, small or big, okay, can do better in expectation for any finite variance distribution. Now, this result was just extended at this Sigmetrics to say that for an infinite variance distribution, you don't even need the load less than half. You can get rid of that. So this is really, really recent work that I'm talking about. But okay, I'm going to move on. So we're done with single servers, 4 questions down, a whole bunch more to go. We're moving to multi-server. Yes?
For clarification on some terminology.
Sure.
On the previous slide, what was the definition of load again?
Definition of load? So load is the fraction of time that your server is busy. So suppose you have 3 jobs coming in per second on average, and each job on average takes 1/4 of a second, okay? Then your load would be 3/4, because 3/4 of the seconds the server is busy, and 1/4 it's free, okay? So in this case it would be lambda divided by mu, but yes?
And do we need to know what m/g/1?
Oh, yeah, I didn't say that in there. So MG1, that's just notation for a single server queue where the job size distribution is general. It can come from any general distribution. And this happens to have Poisson arrivals in here. But a lot of this generalizes even when you don't have that. But yeah. M denotes a Poisson process of arrivals. And the G is for general job size distributions. But what I'm actually talking about is not even general job size distributions. I'm talking about this, heavy tail job size distributions. So it was a little misleading. Yes?
So for that, you make no assumption about the distribution.
I do actually. So here, this result here is stated, this whole sequence here is, I'm making the assumption that you're in some kind of high variability distribution. But this result here, no assumption about the distribution is made.
Time.
Well, sure. I mean, I'm assuming I can implement SRPT, and I'm saying if you implement a policy like shortest remaining processing time, if you knew the size of the jobs, and you went ahead and always ran the job that has the shortest remaining processing time, so you always gave it preference, then you wouldn't actually be hurting the long jobs, believe it or not. Okay, and I can explain that maybe as we keep going. Let's make a little bit more progress. I got to stop questions for a moment. Okay, we got to keep going. Okay, so multi-server systems. Multi-server systems are all over the place. They're becoming very, very popular. I think even Microsoft is getting into the whole multi-server system world, okay? The server farm. Why do we like server farms? We like them because they're cheap. Instead of one fast server, you have a bunch of slow servers, and they're scalable. You can scale up, you can scale down your capacity as you like, okay? So it's a good thing to have. And in these server farms, what happens is usually you have this front-end dispatcher, some high-speed router, that immediately takes the request and dispatches it to one of these servers. So it either runs here or here or here. And I'm going to assume the servers are all identical for the duration of the talk, because it's hard even with the servers being identical. Okay, so there's really two models of server farms. The first is where the servers are handling the jobs in first come, first serve order. So once you dispatch to a server, the jobs there are being handled first come, first serve, one at a time. And there are many cases where that happens. Like in manufacturing, you can't stop a job once it's running. Okay, you finish it, you run it to completion, then you start the next job, because you don't tell a customer, wait, I'm going to go to somebody else. Okay? In supercomputing also, they don't timeshare. They really run one job at a time. And it sounds like some of the jobs here in Microsoft, there's a lot of that too, where you finish a job, like you're looking up this URL. This is some of the stuff I was hearing about this morning. You finish looking up the URL, and then you move on to the next URL that you're looking up. Okay? So that comes up. So this is one model, and I'll talk a lot about this. Okay? Another model is where these guys are commodity servers that you've just put together. These are processor sharing servers. This comes up a lot in serving like HTTP requests, where the connection is sent over to one of these servers. That server handles the connection. And then all the connections that this server is handling are time shared. So you're serving all these files together simultaneously, a little bit of each one. Okay, time sharing between them. So those are the two models. And I'm going to start by going to the first model. Okay, so everybody got it in their head? First model? All right. Okay. So here in this first model, which is first come, first serve, I have a question. Okay. And the question is it better to have one server here, okay, one server that's a fast server, or to have two servers that are slow servers, so they're each running at half the speed? This shouldn't actually be here yet, but okay, two servers each at half the speed. And I'm going to assume here that you have some kind of smart dispatching policy. So I don't know what it is yet, okay, but it's something smart that says which jobs, you have some way of deciding how to send jobs, maybe random, maybe something else, okay, and maybe round robin, I don't know. And these guys are each half the speed, and this guy is very fast. Which is the better system to use when you have a high variability workload, as we have? When it has to send it. Well, if you want to talk about it holding it, come back in 1 second. I'll let you talk about that. But let's say it has to dispatch it. Would anybody like to say something about which is the better system? Yes? Under a high variability workload?
I would guess the right one.
The right one. Oh, from your perspective or mine? The fast server or the two slow servers? Two slow servers as opposed to one fast server? Okay, why?
Well, because you're not. Well, my intuition was you're not held up as long.
Effectively
jobs,
time
but I guess
shared.
it's true either way.
Yeah. You got one fast bunny versus two slow turtles. They're coming your way. There are 12 slow turtles in there, by the way. Okay, so let's discuss what exactly is going on there. Okay. I can keep the bunny if you don't want the bunny. I like the bunny. Okay. You can keep the slow turtles. All right. Under random dispatch, when you're randomly dispatching jobs, what would happen if you were randomly dispatching? Then you would have lambda and mu, versus if you randomly dispatched, you would have half lambda and half mu. What would happen if you did that? If you compared this system, which is random dispatch here, versus this system, which would be better, this queue or this queue? Anybody have that double mint gum? Which would be better, this queue or this queue?
Same answer here.
This queue. Okay? So this queue is better for response time, right? Because it's double the mu and double the lambda, right? So hold on a second. Under random dispatch, this is the correct answer, not that one. Okay? Well, let's move on. Okay? Well, that was random dispatch. Let's move on to something a little smarter. Suppose instead what you did was you dispatched where you send to where there's the least work left. Okay? So you're a little smarter. You look at how much work there is and how much work there is here, and you always send to where there's the least work left. Okay? Now it turns out that which is better, one server or two slow ones or three even slower ones or whatever, depends on how variable your workload is and how much load you have. For a very variable workload, it's better to have more servers because of exactly what you said. When you have more slow servers, you at least let the small jobs not get stuck behind one big job. Okay? And so some benefit is given to the small jobs not getting stuck behind a big job. Okay? Now, your question about the central queue, have you figured it out yet? If you wanted to have one central queue and not the special jobs, do you still like it better? I'll come back to you. I'll come back to you. Yeah, we'll come back. Okay, so that's this policy, okay? Now, could you think of an even better policy for what you would want to do, even better than this? Remember, the whole reason why this is getting better here with the slow servers is, yes, so what would you really like to do?
Send the short jobs to one server and the long jobs to another.
Short jobs to one server, like in our express lane, and long jobs to the other server, right? Okay, coming soon. Okay, so here, if we send short jobs to one server and long jobs to another server, we'll see that in this type of system, when you have high variability, the multiple servers can be way better than, the multiple servers are way, way better than a single server. Okay, and so the impact is that the best architecture can actually end up being a cheaper architecture if you are running your jobs one at a time, first come, first serve. Okay? So as a summary to that, we have questions like this that come up all the time, which is you have some kind of arrival process, you have a router, and you have first come, first serve servers. And you have some kind of heavy-tailed, highly variable jobs. And you're asked to rank policies like which is best, random assignment, join the shortest queue, which is where you go where there's the fewest number of jobs, least work left, which is where you go to where there's the least work, or size-based splitting, which is where you send the shorts to one queue and the longs to another. And which ends up being better? Size-based. Okay, so this is coming on through. All right. Coming on through. Oh, the suitcase. The suitcase had a little bit of problems in the airport, but you'll soon understand why. Okay, so this is how you think about these kinds of things, okay, is that size-based is a good idea, all right? Now, okay, so this is the ranking. So now I ask you this. Suppose you are going to use size-based splitting, where you're going to send the small jobs to one host and the large jobs to another host. Okay, suppose we're going to do that. How do we decide what's small and what's large? What do we do there? So the question here is, do we want to balance the load? So you have a system like this where you've split them up smalls, medium, larges, extra larges. Okay? And you now want to decide whether you should take the job size distribution. This is the density of the job size distribution. I promise no more math, but that's it. Okay? X times f of x, so now that's the work. And equalize it. So in other words, do you choose the size cutoffs so you have equal load being sent to each bucket? I see nods for yes. Or do you not? And we have a scale here that goes with this question. The scale to balance. It's very good at balancing. I could use this in my kitchen, too, if nobody gets the answer. So.
But there's only two answers, so how come I not get it?
Well, it's unfortunate. Do you want to balance the load? No. You don't want to balance the load. All right. You're the first to say no. All right. The scale is yours. Somebody will be happy in your family. All right. So, okay. So recent research has shown that despite all these zillions of load balancing papers, if you have a distribution, so by the way, this is a really hard thing to analyze. So maybe I'm making light of it, but I think the reason that the research is so recent, like this is all 2006 papers, the reason that it's so recent is this is really hard to analyze, this kind of stuff. So the only analysis that we've done is with like 2 queues and looking at whether you should balance or not balance the load. And usually lots of approximations have to be made along the way to try to help you out. But if you have a job size distribution like this, where the probability the job size exceeds x is proportional to x to the negative alpha, this could be x to the negative 1, like 1 over x. Depending on this alpha criterion, you may want to balance or unbalance, but almost never balance. So if this alpha criterion is less than 1, which means a super, super heavy tail distribution, like the fattest of fat tails, okay? If it's less than 1, you want to unbalance, and you want to favor the small jobs. So you want the small jobs to be running under extra light load, which might make some sense because you want to help them out, okay? Because most jobs are small, so most jobs are at the small server, and you want to help them out by running them on a really light load, okay? And that will be the best for the system overall. Choose a cutoff so that the small jobs are receiving less than half the load, okay? If alpha is equal to 1, you want to balance. If alpha is greater than 1, you want to unbalance again, but this time you want to favor the large jobs. Okay, and this is still a heavy tail distribution, but it's less heavy tail than that one. And we still don't really understand this. Okay, I mean, I can explain this. I can show like the math of why this comes up. Where here, the large jobs start to be penalizing you, and you need to run them at a lighter load. Okay, but this is like a whole area of research that's just coming up. Is this understanding of balancing and unbalancing, and I think the reason is the math is hard for it, which is why little has been done. But the impact is we may want to go and rethink those load balancing policies. Because when I say unbalanced, I don't mean slightly unbalanced. I mean way unbalanced. So you can improve performance a lot sometimes by unbalancing. Yes?
You have more than 2 queues.
Yeah. I can't do the analysis yet. But I'm assuming you still want to unbalance.
Do you have experimental results?
Yeah, that say unbalance. Yeah, yeah. Now, this assumes the servers have the same speed. If the servers have different speeds, you almost always want to unbalance. Okay, that's guaranteed. But even when the servers have the same speed, you want to unbalance, which is a little counterintuitive. Yes?
Is there any debate on whether EFT is the thing that you want to optimize?
Yeah. There's a lot of debate on. So EFT is the most popular thing that people look at to model, to try to minimize. But there's also EFT squared, the variability. Okay, and there's also mean slowdown, which is something else that people look at. So slowdown is you take the response time of a job, but you weight it by dividing it by its size, by its service requirement. So a small job should have a small response time, and a big job can have a big response time. And because, if you're a big job, you're maybe willing to wait longer, and small jobs are willing to wait less. Those types of things, trying to minimize slowdown, is actually similar to the same results that we're getting here. But yeah, there are 3 metrics, basically, that go around that people talk about. Oh, my God, 3 hands went up at the same time. Yes?
Just curious. So are there results on when the number of servers go to infinity?
Oh, yeah. So that's the easier thing to analyze is the number of servers go to infinity. So I don't know particular results about balancing or unbalancing, but there are other results on servers go to infinity that give us indications of what we need to do and stuff. That's an easier case to analyze is the number of servers go to infinity. Yeah, there are all sorts of approximations based on that kind of thing. Yes?
Following up on the earlier question of what it is we're trying to optimize, is there an easy way to sort of take into sort of a value effect, like big jobs are worth twice as much as small jobs, or you now have a...
Right, there is an easy way to do that, yeah. So that's easy to factor in. It's just the analysis itself is hard. Analyzing these scheduling policies is hard, as we're going to see when we get to the next slide. So let me show you one more thing. So far we've been dealing with these first-come, first-served systems, and I promised you that the world doesn't all look like that. So you could instead... Oh, so this was just a reminder. Right? This is how they are ranked, the scheduling policies, 1, 2, 3, 4, right? For first come, first serve. But you could instead of this first come, first serve type system, you could instead have processor sharing at your servers. Like in a web server, web server farm, where the jobs come in and you send them. So Cisco has a product like this that seems to sell for about $32,000. That's the Cisco local director, and it has 32 of these servers. I guess that's where the number comes from. And they do processor sharing, okay? And IBM has a product called the IBM Network Dispatcher. I had a really hard time finding a Microsoft product. This is the only one that I could find that was something like this. I'm still not entirely sure. Maybe you can tell me. Okay, this SharePoint. But anyway, many companies seem to have this type of product. And the question is, when you have processor sharing servers, okay, this is called the server farm. So this is what traditionally people mean when they talk about the server farm. And here we have a nice farm to go with our farm. So when we have this server farm, we also want to understand what happens if you use random dispatching as opposed to join the shortest queue, which is the fewest number of jobs, as opposed to least work left, where you look at which host has the least total work, okay, as opposed to size-based splitting, where you split up small jobs and big jobs. But now you have processor sharing at each of the servers. So the question is, does the answer change? Remember before, this had the highest mean response time. This was second highest. This was third highest. This was fourth highest, right? I mean, this was the best. This was the worst. Okay? Now my question is, what should it be for this system? And this is where the math gets hard, is analyzing these things, by the way. But yeah.
Splitting shouldn't help that much anymore because you can split in each of your...
Okay, splitting doesn't sound like it should help that much anymore because
Well, you already can split.
you're kind of splitting in here and how you're serving things. So that's a very, very good point. Is that these processor sharing systems already are time sharing, so they're letting short jobs through. Okay? So what is your feeling about this?
Join shortest queue would be pretty good.
Least work left is the best.
Least work left is the best? Join the shortest queue is the best? Server farm. Join the shortest queue. Okay, so it turns out that, and you had the right answer at the beginning, so maybe you got to share that with him. I don't know. Random and size-based are provably equal. Okay, they're exactly identical. Number 1 and 4 are the same thing in this case for mean response time. Join the shortest queue is way better than least work left because think about it as a greedy strategy. When I come into the system and I see, I don't know how many of you are here, 40 of you here, okay? So I walk in and I see 40 of you here, okay? Then I have to share with 40, so I'm getting 1/41th of the system. As opposed to if I went and I shared over here in this queue, maybe there are only 3 guys here, so I'm getting 1/4 of the system. So I'm getting a much better share of the processor if I go to where there's the fewest number. I don't care about the total work. I care about the number because I'm sharing with you guys. Okay? So now this policy has eluded researchers for forever, basically, how to analyze this policy. And nobody's even tried it with processor sharing queues, which makes it worse. But we have the first, I guess you can barely see this, we have the first analysis of this that's unpublished, but it's with Ward Witt and Carl Sigman at Columbia. This is a grad student of mine, Varun Gupta, that actually looks at this system with join the shortest queue and produces numbers of how good the performance is. And it is way better than the other policies. But I think you can still do better than that. So that's one of the areas that we're working on. Yes?
Can you really ignore the total amount of work that are in the queues? Like if the 40 people here each have tiny, tiny jobs, that, and like the 3 people are going to be have really
right. So let's think about that. Let's think about that, right? Okay. So this is very different from the supermarket aisle. Okay. So remember the supermarket prize went to you over there, right? Supermarket was first come first serve. In the supermarket, I really care about how much they've got in their baskets. Okay. But here, if I go to where there are 3 jobs, I get 1/4 of the server. Okay. So if my job is fast, it'll get done. It's just finished. We're done. Bye bye. Okay. Whereas if I go to where there are the 40 jobs, I get 1/41th of the server. If my job is fast, it'll still take 41 times its size. Okay? The other guys may or may not still be around. Now, I guess you're saying maybe if the 40 jobs are so fast, they'll all be gone. But other jobs will, chances are, come and take their place because we're in some steady state system. So, yeah. I mean, okay, maybe you could calculate a little more finely about whether they're likely to be gone. But basically, you're counting how many you've got. That's it's a good policy. Okay. So we're done with single server. We're done with multi-server. And what we're going to do now is we're going to do the hardest of the hards, okay, which is we have multiple servers, but there are dependencies between the servers, okay, which makes the problems worse, okay. All right. Okay.
Cockroaches in your house, then you want to win this, right?
Yes. This is good for cockroaches. So the model that I'm going to talk about, that just because I've done a lot of work in this model, is the N sharing model. And this has been studied by a long, long, long list of people, too many to name. Okay? And the N sharing model works like this. There's this person, Betty, okay, the beneficiary. Well, I call her Betty. But, okay, so Betty is sitting here, okay? And she's working on her queue of jobs. So she's got jobs that she's working on, okay? And this guy, Dan, over here, and Dan, the donor, is working on his set of jobs. And the reason we call Dan the donor is he's like some very fast machine or something like that, okay? And so he, in addition to doing his jobs, can be also helping out with Betty's jobs. Like maybe when he's free, he can work on some of Betty's jobs or something like that. And he's capable of doing both types of jobs. So this is some kind of machine that is capable of doing both sets of these jobs, whereas Betty can only do this set of jobs. Okay, but Dan is actually able to do both sets of jobs. So this kind of stuff comes up in computers with this notion of affinity scheduling that you might have heard of, where Betty's jobs have some affinity for Dan's server, and they might, she might want to send some jobs there, or because they can be run faster on Dan's machine for whatever reason. Or it comes up in operations research a lot, in linguistical applications, where Dan might be a bilingual server who can speak 2 languages, so he can handle the English jobs that are coming to Betty and the French jobs that are coming to him. But he can also help out with English jobs, so he can speak both languages. So he can do English jobs or French jobs, and Betty's doing the English jobs. And so this is the type of system that comes up. And the questions that we have is, how much helping should Dan do? I mean, they're cooperative. They're working together. They're on the same team, okay? So they're on the same team, and some of these jobs can go over here to just be offloaded over here. And the question is, how many? So one possibility that we use in systems a lot, oh, by the way, this is an N sharing model because it's the N. Okay, that's what the N is there for. So, okay, so one possibility that we use a lot is this notion of cycle stealing. And cycle stealing is this concept where the donor over here is helping the beneficiary with her work whenever he happens to be free. So he does his work, but whenever he happens to be free, he'll then take on some of her jobs. And he does, one job at a time from hers until he gets a job, and then he goes back to doing his jobs. And this is what we do in computer systems all the time. We do this cycle stealing type thing. But the question is, could we do better, okay, by being more aggressive with Dan's help? So could Dan be more aggressively helpful? Like, for instance, could Dan have to help Betty sometimes even when he has some jobs, just because it might be the right thing to do, okay? And these mu's here denote different service rates. So this is the rate at which Dan serves his jobs. This is the rate at which he would serve Betty's jobs. This is the rate Betty serves her jobs. So, you can imagine conditions under which Dan is such a fast server that it might be good for the system overall if Dan helped Betty more aggressively. Yeah, there is FIFO. Yeah, these are, FIFO or FIFO. Yeah, this is a FIFO and this is a FIFO.
You try to mimic a little bit putting the large jobs to Dan or Betty. You can sort of choose and the small ones on the other side. That might work.
For example, that's one way, right? Or, but even here, even in the case of exponential service times, you'll see that there's a lot of improvements. There's a lot that you can benefit by having Dan be more aggressive. But yeah, it has something to do with smalls and larges too. Okay, so Dan might be more aggressive with his help because of the way that he serves jobs and he can get them done fast. And maybe that's better for the system overall for him to help even when he's got some of his jobs waiting, if Betty's got enough jobs. And so the question that we have is, how can we do better with these threshold policies? So here are your choices. And this question has to do about control. Who gets control? Oh, we have handcuffs. Who gets control? These, by the way, are genuine handcuffs. These are not toy handcuffs. Okay, these are the real thing from the police department. Okay? So, they were not carried on. So, this is a pair of genuine handcuffs. And the question is, should the man or the woman have control over the threshold? Now, let me explain what I mean by that. Okay? So to make this problem more concrete, okay, they're both working cooperatively to get work done in their house, lots of housework. And Betty is doing housework, and Dan, too, is happy to do housework, right? So Betty's doing her housework, and she says, I will do housework, but I will not do the cockroaches. Okay, the cockroaches I don't touch. That's your job and your job only. I don't get near the cockroaches. This, by the way, I was working on when I was in New York City doing my sabbatical, so you can understand where this all comes from. Okay, now Dan over here, okay, Dan, he does all the cockroaches. See the cockroaches? They're straight into Dan's queue. That's his work, right? But in addition to cockroaches, let's face it, they don't take up that much time, the cockroaches. Okay, he can help with Betty's jobs, right? Okay, all the rest of the housework in addition to the cockroaches. And the question is, which of Betty's jobs should come to Dan? Like how many of Betty's jobs, what is the threshold point at which Betty's jobs come to Dan? Okay? So one possibility is this thing called the Betty side control, the beneficiary side control, which was a policy proposed by some people at IBM and also by some people in San Diego. And it says that the beneficiary, Betty, should have control. And she should have control in that she should set a threshold. And she should say, whenever I have more than T Betty threshold jobs, you have to help me, period. I don't care what you've got. I don't care if you're idle, not idle. I'm going to control the story. And whenever I have more than T Betty jobs, then you help me out. You start taking jobs. Okay? The other possibility is we could give Dan the control, okay, where Dan has a threshold. And he says, well, whenever I'm below this threshold, then I'll help you. Notice this is more aggressive than cycle stealing. He's not saying when I'm idle, I'll help you. He's saying whenever I have less than 5 jobs, then I'll come help you. Okay, so it's more aggressive than cycle stealing. Okay, we haven't asked the question yet. Okay, so what we're trying to do is minimize the overall mean response time. Okay, and again, we have the choices of Betty having the control or Dan having the control, and we're trying to minimize the mean. Are you ready to answer? One question.
A controller in the system that then decides on a basis of both? Like
God controls.
God control. Okay, well, these are the 2 options I'm giving you. You're right. There might be better ways to do this. But right now, we're trying to decide, does the woman have control or does the man have control? Are we ready to...
My husband said the woman has control.
He said the woman has control. And he is right. Okay? So the woman does have control. Okay. Let me talk a little bit about this problem. Okay. So this is one of those things that's surprisingly been very hard to understand, is these policies. And the reason these policies are hard to understand, okay, just to bring back some of the math world here, the reason these policies are hard to understand is that when you're trying to understand a policy like this one or this one, you need to actually track in your Markov chain the number of Betty jobs and the number of Dan jobs. You need to track both types of jobs, Betty jobs and Dan jobs. And so what you end up with, so these are not cockroaches, by the way. What you end up with, these are states in a Markov chain. Okay, what you end up with is you end up tracking the number of beneficiary jobs and the number of donor jobs. And so you end up with this Markov chain that's growing unboundedly in 2 dimensions, okay, 2D infinite chain, which nobody knows how to analyze. So what people sometimes do is they try to like just truncate the Markov chain, okay, but that doesn't give accurate answers. So we've come up with this technique at CMU. This is with a colleague and some students, that deals with what do you do when you have these 2D infinite chains. And it allows you to, this technique, dimensionality reduction, allows you to analyze chains like this with accuracy to about 1%. And, 1% error. And so it allows us to analyze this kind of policy and that kind of policy and really see the difference. And it is amazing how much better it is when the woman has control. I mean, just unbelievable, irrevocable, not even close, yes?
Which is, Q lengths are bounded in real life, so...
Yeah, so Q lengths are... Right, that's true. And so you might say that, but if you really did bound these to what the Q lengths were bounded at, like maybe 1,000 or something like that, then the Markov chain would just get too difficult to analyze sometimes. So it's important to be able to analyze it in the unbounded case. But yeah, if it's bounded, then you can definitely, chug through and try to analyze this very, very large Markov chain. But yeah, it's a good point. I mean, Q lengths are bounded. So, okay, so back into this who gets control. As we said, that the mean response time is minimized when the woman has control. And the reason is, just for a little bit of intuition, okay, aside from her being a woman, okay, the reason is that she's the one who's getting the help here, okay? And so it's better for her to say when she needs the help. than for somebody to tell her when she's getting the help.
But it's just the extension of the freeness, right?
It's the freeness, yeah.
I mean, freeness was not the best, so why should best set, I set a little different threshold,
right.
It's not freeness, but almost freeness.
Right. Yeah, that's a good way, very good way of putting it. Yes?
Are there like established optimal values for TB and TD?
So that's hard. So now that we can do the analysis, we can do the analysis with different values. We still can't do the analysis with an open parameter, but we can do the analysis with different values and look at what those values are. And I'm getting to that question right now. Like, we can try it with different values and see what happens to response time.
How can you know which policy is better without picking values?
So we can experiment with all different values. We can plug it into our Markov model, you know, all different values, the whole range of values. Yeah, we plugged it in. Yeah, well, you'll see it's smooth curves, so it's not like we need every possible point. They're smooth curves for this kind of analysis. Okay, but there's still an interesting question that comes up, which is the question of robustness. Okay, so this talk is almost over, by the way. We're almost at the end. The question of robustness. So in addition to mean response time being important, you also want to make sure that your house doesn't get flooded by cockroaches. Okay, because suppose you have Betty doing the controlling. Okay, all right, so suppose you have Betty doing the controlling, and she says, come help me whenever I have 5 jobs. Okay, these cockroaches now are building up because Dan is going to help Betty, and maybe his queue is overflowing, okay, with cockroaches, which isn't helping anybody, okay, and getting the house clean. So what we really want is we want a policy that's robust against misestimating the load, okay? So in other words, suppose Betty was sitting there, okay, and was saying, I want you to help me whenever I have at least 5 jobs, and she assumed that Dan's load was such that he could handle that, okay? But really she got his load wrong, and his load was higher than he thought, okay? If his load was higher than she thought, then, the handcuffs are getting too much attention. If the load was higher than she thought, then the house could get overrun by cockroaches. So the question is, how are we going to deal with this robustness issue? Which policy is the more robust policy, and why? Which is more robust against misestimation? Yeah? Pardon me?
Where the man takes control.
Where the man takes control, right? That's more robust. Because that can't cause things to go to infinity, okay? Because basically, he's not going to go to infinity because as soon as he gets to a certain number of jobs, he just cuts off helping, right? And so he hasn't gone up to infinity, right? Okay, but I'm not going to give you this yet, okay? Okay, whoops. Okay, but suppose I now want to both have protection against misestimation of load, but I still want to get the good performance that we had when the woman had control. So we want to let the woman have control, okay, because we know that that minimizes the mean response time.
She should have input, not control.
Input, okay. She should have input. Okay, let's be very fine-tuned here. We want to let the woman have input. At the same time, we want the robustness and protection of the donor side control. What should we do?
Policies.
You want to have both 2 thresholds, 1 and 2?
Well, with different priorities. So,
by the way, if you have 2 thresholds, it just disintegrates to the man having control. So what do you want to do? Yeah?
So the priority 1 policy is when CD goes beyond, you have more.
Good.
Then you cancel the other policy.
Good. That's exactly the point. Okay, so you want the man to have a control here. You want him to have a threshold. And when he's below this threshold, okay, then he's feeling good, so the woman can pick a very harsh threshold, okay, and be very harsh in her threshold. But when he's above his threshold, he's got too many cockroaches lined up, then she has to pick a much more conservative, higher threshold, okay? I'm going to pass this on down. So what you really want is you want to have 2 thresholds. Can we pass that on down? Raid is coming down. Okay, we want to have 2 thresholds on the beneficiary side. Okay, where the donor determines which of the 2 thresholds. Aren't you glad you didn't win that? Donor determines which of the 2 thresholds on the beneficiary side you use. And so this is what actually happens here in practice, is that this was the harsh threshold. This was when Betty set a threshold of 6. And so she can get really low response times here. But as Dan's load increases, this goes to infinity. So this can be very unstable if she misestimated Dan's load, which was maybe over here. Okay? This is a more conservative Betty threshold, but it's not as good down here in the low lows. And so what you really want is this adaptive dual threshold policy with the two thresholds, and you can actually meet both goals. You can get the low mean response times over here, and you can get the conservativeness of the robustness, and you can do both, and it's nice. And yes?
More must be better, right?
That's one thing we're trying to figure out now. So we're trying to do the analysis to figure out how many are really necessary. 2 is very good. 3 is definitely better, but the question is how much better, and when do you stop getting this gain? Okay, so the impact was robustness is equally important to efficiency. Maybe it's more important than efficiency. I don't know. Okay, conclusion. We've covered many themes in systems design. We covered capacity provisioning. Be careful not to over-provision. We covered heavy-tailed workloads and how they actually affect scheduling as opposed to exponential distributions don't affect scheduling. We covered whether it's better to have one fast server or many slow servers, and we saw that that makes, that there's real answers depending on what dispatching you use and what model you use. We covered load unbalancing. Definitely unbalance your load. We covered server farms, and we looked at processor sharing server farms, but we also looked at first come for serve server farms and saw that the supermarket was pretty good in the first come for serve server farms. And we covered threshold-based resource sharing, which is a really important theme in systems. And we covered robustness. Okay, so that's all we managed to do today. If you want to know more, I have lecture notes that are online for my course. They're being used by over 1,000 people worldwide. And this is the course number. You just go to my webpage, and I have lecture notes on there. And for those of you who have taken this course, it's hard. But anyway, you can go look for it. Okay, that's it. Questions? I finished just in time.
Just curious, is it possible to model the multi-server system as a MIMO system, multiple input, multiple output, like something as noise, something as channel, following possible things from the communications?
Okay, so you want to have multiple inputs, multiple outputs for them?
Kind of similar to me.
Is it term from control theory? MIMO systems are term from control theory.
Yeah, control theory is a really nice complement to queuing theory to try to understand what goes on. But they're also somewhat different. So the control theory is good for trying to understand how to adapt the threshold and things like that. Queuing theory is good for the long-term stationary behavior of what happens, in the long run if you look at mean response time or something like that. I think they're best used together. I don't know. I encourage my students to take classes in both. Yes?
So in that related to this question, so all this result assumes that there is fixed arrival rate, or it's also, in reality, actually you have the algorithm, and then the rate changes over all the time.
Right. So you're talking about this kind of thing, this type of result. Right. So if the rate... Right. So I'm not dealing with worst case. I'm dealing with stochastic, IID type of inputs. This question about rate changing is something that we've actually studied in the same paper that we published on this type of stuff. We looked at the situation where the arrival rate changes over time and the service rate changes over time. And what we looked at was both this rate changing and this rate changing. And what we find there is that whereas before it was clear that Dan was the more robust policy, was when we had the more static world, it was better to go with Dan's policy. Now it's not so obvious once things change what really is robust because things are changing. It's not, it depends on conditions. So yeah, so changing things changes. Yeah, so here in this problem, what we've assumed is that basically Betty and Dan each have some kind of load, but Betty might be misestimating Dan's load in setting her threshold. If she knew it exactly, she should just set it. The whole world would be good.
And in all the previous results that you described, it also assumes that there is a fix, right?
Yes.
Yes. If things changes, then
yeah.
all these policies are
yeah,
not.
I think we're the first ones to even look at varying the arrival rate. Yeah. Other questions? Yes?
There are also some interesting problems in practice when you have things like lock contentions or lock convoy problems. Are there any studies around
when you have low contention?
Contention.
Lots of contention. Lock contention. Yeah, what about lock contention?
So sometimes the goal is not to minimize E of the average completion time, but also to make sure that the system will not get in a state where it can get out hard, which, for example, the lock convoy problem.
Right, right. That's not really related to any of the stuff that I'm talking about. I do know what you're talking about because I actually worked with database locks. We've done some database lock queues, not on that particular problem, but more on the performance end of it, where the issue is that the guy who's holding the lock sometimes can be blocking a lot of other transactions and can be holding it for so long because he's not only holding the lock, but he also gets into another queue where he's waiting in queue for yet a second lock. So then he's holding 2 locks while he's still waiting in queue, and other people are waiting behind him, and that can be a real problem. And
means that this essentially means that service time depends on the load, depends on the queue size. For example, when you have a single item being serviced, then you have one service time, but when you have like lots of stuff.
No, we don't talk about it that way. We still talk about you having an individual service time, but it's your response time or how long it's taking you is being affected by the fact that one guy's holding a lock and that the queue is long, so you wait through a long queue. Your service time is how long it would take for you to run if you were alone in the system. That's the definition of your service time. Okay, what you're talking about is your response time being long. And no, okay, you'll have to ask me offline. Okay, yes.
So there's a lot of lines in the real world where, yeah, you can't reorder people like grocery store lines and so forth. But in the computer world, it seems like you could also reorder jobs. They don't have to be done in the order that they arrive.
That's true.
Does queuing theory look at that? Like,
yeah, of course.
Not just all in parallel or just in order, but also like,
let's go here. Yeah.
If you had a pool of jobs and you're just allowed to pick which one job do I want to execute.
Sure. That's absolutely what we look at. So here you are in this model, right? And you're saying instead of immediately dispatching to one of these queues, you want to hold on to the jobs? Good. Good. So yeah, so that's a very reasonable question. So what you might want to do is you might want to have one pool of things over here. I guess this is related to your question. You might want to have one queue, okay, and then these guys, whenever they're free, they just grab a job, right? Now, I understand. If your queue is a first come first serve queue, then this policy would end up being equivalent to this one, least work left. Okay, it ends up sending the same things to the same places at the same time. Okay. However, you could be more clever, and you could have your central queue do something like shortest job first, where you always pull out the job that's shortest and run that first. And that policy sounds like it's very, very good because now you have a central queue, and you can always pull out the job that you're going to run. It's the job that's shortest first. Okay, so you pull out the shortest one first to run that one. That ends up being really good, except it's still not as good as breaking up the jobs by size, small and long, assuming that you can't preempt jobs. If you're allowed to preempt jobs and do in this queue SRPT and then have these servers, then that policy is extremely good. It has not been analyzed in the stochastic setting. You might think it's the optimal policy. Like you guys might be thinking, the best thing I could possibly do is to have one central queue. It's doing SRPT. I have these servers, and they always grab the job that has the shortest remaining processing time and run it, right? That sounds about as good as you can do, right? Because you have this queue, SRPT, you got these servers, they grab the shortest remaining processing time at any point in time, they put it back, right? That sounds perfect, right? That's been analyzed. That policy has been analyzed by a lot of people in the Fox stock community. I have references in another talk. But what they proved was that that policy, it's not optimal, okay, but it's close to optimal in competitive ratio. And the competitive ratio is you look at the biggest job size divided by the smallest job size. So if the biggest job size was like 10 to the 7 and the smallest job size was 1, you look at that ratio, so that's 10 to the 7. And then you take the log of that. So that would make it 7 competitive if the difference between the biggest job size and the smallest job size was 7 orders of magnitude. So it's the log of the ratio of biggest over smallest. That's what they were able to prove about the policy. In practice, I think it's way better than that. But that's what people were. Yeah, as compared to the optimal. As compared to the offline, you know everything. It sounds like a really, really good policy. And I bet it really is a really, really good policy. But the best that the community has been able to show is that ratio as compared with optimal.
Like that means
okay.
some competitive means it's within A factor
competitive
of 7.
means within a factor of 7 of optimal is what they've been able to show. That doesn't mean it's not within better than a factor of 7.
That's what it's like.
Right. But that's the best policy people have been able to think of, is to have one central queue and then the servers. And one thing that was nice was a recent paper that came out. I think it was by Ozer or something, and it was pretty recent. Yeah. So, oh, is that? So. Oh, for validation. Oh, good. So, okay. So you can tell I'm not lying. You can tell I'm not lying. So the recent paper that came out. Boy, I wasn't prepared for a whole lecture on this, but a recent paper that came out said, suppose you want to achieve that, having that central queue with those servers, but you want to achieve it by still doing immediate dispatch. So you still want to just immediately dispatch your jobs, but achieve the sense of having kind of that central queue. So it turns out you can do that. And I think the name of the algorithm was IMD or something. And what it is when the jobs come in, you want to dispatch them in such a way that there are enough short jobs at each of the servers. So you break the jobs into size classes, and all the smallest size jobs you want to make them equal among the servers, and then the medium-sized jobs equal among the servers, and the large jobs, so that each server kind of is doing SRPT and has enough short jobs to kind of keep it happy and stuff like that. And that policy was had a very similar competitive ratio, the same biggest over smallest, and take the log of that. So the log of the ratio of biggest over smallest had the same competitive ratio as the central SRPT queue. And so that was a nice result. And yeah, I don't know. There's no prize. I know. Well, I didn't prepare for questions. Questions could be on anything. So, all right, more questions. Yeah.
So in the supermarket, they use size-based splitting, but ignoring that, because most of the lines are just the least work left kind of style.
Yeah.
There's two ways. Most supermarkets just force you to get in the line right away, but which is equivalent if you could exactly predict the least work left. But in practice, it's not robust because you can't. So why don't more people?
Why can't you predict least work left? Why can't you see what's ahead of you? You don't care about who's coming after you.
Paying with a credit might be paying.
Oh, okay. So you can't really see. Okay.
So why don't they use the Fry's electronics model, which is exactly the same but is not subject
to have you have a central queue and then pull from the central queue.
And you get that.
Yeah, that would be good. Yeah, that would be better. Maybe it would make people feel worse. I don't know.
Borders, bookstores, for example.
Yeah. Well, banks sometimes do that, or airlines. When you go and you wait, they have the many airline tellers, and you have one queue. They use that.
But is there some advantage to the supermarket model to force
takes less space. Yeah. Which matters if you're pushing shopping carts around. That's why they can do it in banks and places where you.
There you go.
But you can always take a number like the old days.
Yeah, there you go. Yeah, it feels better. I think part of it is just the psychological thing of seeing so many people ahead of you. It freaks people out.
Also, it's probably convenient to have people already have the groceries out onto the conveyor.
The cart, onto the conveyor belt, right. Right.
Oh yeah, the impulse.
Okay. All right. Thank you for coming.